Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial on preliminary alignment checks and corrective measures will discuss information that will hopefully assist anyone who is responsible for installing or maintaining rotating machinery, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So, this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. The major topics in this tutorial will discuss how a dial indicator works, how to perform a shaft lift check, how to measure runout, what are acceptable amounts of runout on rotating machinery, how to determine what is causing the excessive runout and what you need to do to correct it, and how runout is frequently and unknowingly overlooked when aligning the shafts of our rotating equipment. One of the most useful precision measurement tools you should have when working with rotating machinery is a dial indicator. There are several different designs of dial indicators, but the ones most often used are bottom plunger or back plunger type indicators. The stem of a dial indicator is attached to a rack and pinion gear assembly. The back plate of the indicator on the right has been removed so you can see that the stem of the indicator extends all the way through the indicator body. Gear teeth are notched on the side of the stem, and a round gear rotates as the stem translates up and down. This round gear is what rotates the indicator needle, which is currently pointing at 81 as shown on the dial indicator on the left side of the photograph. When the stem of the indicator is pushed in, the needle rotates in a clockwise direction. A spring in the indicator pushes the stem back outward. The number dial, which is also called the bezel, can be rotated so you can zero the indicator. If we take a dial indicator, position the tip of the stem of the indicator so it is touching a surface, and plunge the stem inward, the needle will rotate in a clockwise direction. If we then move the indicator body toward the surface and stop it at some point, we can then anchor the dial indicator against a stable object, usually by using a clamp or a magnetic base to hold the indicator body in a steady position. If the surface that the stem of the indicator is touching begins to move upwards, the stem of the indicator begins to plunge inward, and the needle rotates in a clockwise direction. Each tick mark is 1/1000th of an inch, so, right now, the surface has moved 5 mils upward, and we can say that we have a reading of +5. When the needle rotates in a clockwise direction, these are referred to as positive readings. If the surface continues to move upwards, the needle continues to rotate clockwise to a +10, then a +15, +20, +30, +40, +50, +70,000ths of an inch. Notice that the needle is pointing at what looks like a -30. This particular dial face is called a 0-50-0 dial face or a balanced dial face. Some dial faces are balanced dials and some are continuous dials. What is important to understand with dial indicators is that the position of the needle is irrelevant. How far and which way the needle rotated when observing the position of a surface is what is really important. We are trying to find out what happened from the starting position to the finishing position of an object we are observing. In this case, we started at 0 and moved the surface upwards toward the indicator a total of 70 mils. If we start moving the surface downward, the needle now rotates counterclockwise, eventually getting back to where we started, with the needle now pointing back at 0. If the surface continues to move downward past the starting point, the needle continues to rotate in a counterclockwise direction to a -10, -20, -30, -50, -60, -70. Yes, I know, the needle is pointing at 30, but from where we started at, the surface moved away from the indicator body a total of 70 mils. If you think you're confused right now, you probably are, so go back through this segment until this is clear in your mind, because understanding how a dial indicator works is extremely important for this and most of the upcoming training tutorials. Not every piece of machinery you work on is brand spanking new. More often, you will be working with rotating equipment that has been running for a while, maybe a long while. One of the questions you may invariably have to address could be, does this machine need to be rebuilt? It doesn't make much sense aligning a machine with damaged bearings, so one of the uses for a dial indicator is to do a shaft lift check. This was casually mentioned in the very first tutorial when we were discussing bearing clearances. To perform a shaft lift check, set the tip of a dial indicator on top of the shaft, plunge the stem in a little bit, and hold the indicator still. You could use a magnetic base, perhaps, to hold the indicator in position as shown in the illustration. Zero the indicator, then lift up on the shaft and observe for any movement on the dial indicator. A long time ago, a very wise engineer I was working with said, if something is important enough to measure, then it's important enough to write it down and keep a record of it. So if you're not in the habit of writing things down, now might be a good time to start. Depending on what type of bearings are supporting the shaft, dictates whether the movement you saw was either bad or good. If the shaft is supported in journal bearings and you saw no movement, that is bad. If the shaft is supported in journal bearings and you saw some movement, that might be good if the amount of movement you saw is within the acceptable radial bearing clearance range. What is the acceptable radial bearing clearance range for that machine? Search me. Hopefully someone wrote that down someplace, like on the machinery data card that you have with you. If the shaft is supported in rolling element bearings and you saw no movement, that is probably good, but you may want to verify that. If the shaft is supported in rolling element bearings and you saw 1 to 2 mils of movement, that might be acceptable, but just to be safe, you may want to discuss this with your engineer or with the manufacturer of the machinery. If the shaft is supported in rolling element bearings and you saw 3 mils of movement or more, that is probably not acceptable, and you need to discuss this with your engineer or supervisor or with the manufacturer of the machinery. I frequently perform shaft lift checks right before or after runout checks. Runout simply describes a condition where a rotating component is off-center or eccentric. To measure a runout condition, set the tip of a dial indicator against the part on the rotor that you would like to check and plunge the stem in a little bit, then hold the indicator steady. You could use a magnetic base attached to the machine case or base plate, or you could use a bracket attached to another shaft to hold the indicator still, as shown in the illustration. Once the indicator is set up, begin slowly rotating the shaft that the indicator is touching. In this case, you would rotate the motor shaft. If the outer surface of the coupling hub on the end of the motor shaft is perfectly centered on the shaft, when the shaft rotates, the needle on the indicator would not move. That, however, doesn't always happen. Let's say we could stick our head in between the motor and pump shaft and watch what happens from an end view. Imagine that you are looking down the axis of rotation of a shaft from an end view. A coupling hub has been installed on the shaft, and we are about to do a runout check on the coupling hub to check for a runout condition. We place a dial indicator on the outer surface of the coupling hub, plunge the stem in a little bit, and hold the indicator in a stable position. Just for an angular reference, notice that the keyway is currently in the 12 o'clock position. So now, let's begin slowly rotating the shaft. As the shaft rotates, notice that the dial indicator stem and the pointer needle is moving. When rotation starts, notice that the needle is rotating in a counterclockwise direction. Remember, these are called negative readings. As the keyway approaches the 3 o'clock position, the needle is pointing at a minus 10 mils. It appears that the outer surface of the coupling hub is moving away from the indicator. As the keyway continues to rotate down to the 6 o'clock bottom position, the needle continues rotating counterclockwise, so when the keyway gets to the 6 o'clock position, the indicator now reads a minus 20 mils. As we continue rotating, notice that the needle is now rotating clockwise, so when the keyway gets to the 9 o'clock position, the reading is now back to a minus 10 mils, and as the keyway rotates back to its starting position at the top, the needle on the indicator returns back to 0. The total sweep that the needle makes is called the total indicated runout, often referred to as the TIR. In this particular case, the needle swept from 0 to minus 20 mils, so the total indicated runout is 20 mils, or another way of saying this is that we have 20 mils of TIR. It is important to understand that this has nothing to do with shaft alignment. I have heard people talking about TIR readings thinking that they have something to do with shaft alignment. They do not. There are some other terms that you need to be aware of. Whenever the needle has swept to its farthest clockwise position, that point is called the high spot. Whenever the needle has swept to its farthest counterclockwise position, that point is called the low spot. The high spot and the low spot should be 180 degrees apart. Also be aware that there is a difference between high spots and hills and bumps, and there is a difference between low spots and flat spots, gouges, and valleys. Hills, bumps, flat spots, gouges, and valleys are talking about surface profile. High spots and low spots are talking about something that is off-center. Here, we have 20 mils of runout on the coupling hub. Is it all right to have 20 mils of runout on a rotating part? Good question. Here are the guidelines that I have been taught by people who manufacture or rebuild rotating machinery. For shafts operating up to 1800 revolutions per minute, you shouldn't have any more than 4 to 5 mils of total indicated runout. For shafts operating between 1800 and 3600 RPM, you shouldn't have any more than 3 mils of total indicator runout, and for shafts running above 3600 RPM, 2 mils or less. For companies who manufacture or rebuild rotating machinery, runout checks are an integral part of the assembly sequence, where runout measurements are taken at several points along the length of the shaft before installing parts onto the shaft. As assembly of the parts ensue, runout checks are also made on those parts as they are installed onto the shafts. So it is not uncommon to take runout measurements on shaft sleeves, pump impellers, wear rings, fan wheels, turbine blading discs, or labyrinth seals. For us, usually the only part of the shaft that is exposed when we are aligning machinery is the part of the shaft that is sticking out from the inboard bearing to the end of the shaft, which is typically where a coupling hub is attached. For example, here is a photograph of a runout check about to be made on the coupling hub on a motor shaft. Keep in mind that the dial indicator doesn't have to be put on top to take a runout measurement. The dial indicator can be held in position at any angular location. Remember, you rotate the shaft and keep the dial indicator in a fixed position. Oh yeah, make sure the stem of the indicator is actually touching the coupling hub and plunged in a little bit. Let's review the 3 most common types of problems that can cause a runout condition that we can actually measure without disassembling the machine. Usually what I do is set an indicator up at the furthest point on the shaft where the coupling hub is located. I slowly rotate the shaft, observing not only the total sweep of the indicator, but also where the needle has swept to its furthest clockwise position, showing me where the high spot is located. Notice that there is 6 mils of runout at the end of the shaft. So this is a little bit more than is allowed, but now I have to figure out exactly what's causing the runout problem. Before I move on, I make a mark where the high spot is occurring. Usually the next thing I try to do is take a runout reading directly on the shaft between the inboard bearing and the coupling hub. Again, I slowly rotate the shaft, observing not only the total sweep of the indicator, but also where the needle is swept to its furthest clockwise position, showing me where the high spot is located. Notice that there is no runout on the shaft. The next thing I do is set the indicator up on the back side of the coupling hub and take another runout measurement there. Once more, I slowly rotate the shaft, observing not only the total sweep of the indicator, but also where the needle has swept to its furthest clockwise position, showing me where the high spot is located. Notice that there is also 6 mils of runout at that point in the coupling hub, and I notice that the high spot there is in the same angular position as the high spot at the end of the shaft. There are 2 possible reasons for this. Either the hole in the coupling hub has been bored off-center, or if the high spots are at the same angular position as the set screw, then the hole in the coupling hub was bored too big, and when the set screw was tightened down, it drew the coupling hub off-center. Another possible runout condition you might see is if the hole in the coupling hub was bored at an angle. In cases like this, there is no runout on the shaft, but there is runout on both the front and back sides of the coupling hub. The high spots will not be at the same angular position, and they may not be exactly 180 degrees apart. The next possible condition is a permanently bent shaft. What happens here is that the runout keeps getting worse and worse the further out you measure on the shaft, and all of the high spots are in the same angular position. So here are the three most commonly found runout conditions that can exist on the part of the shaft that is exposed and we can actually get at fairly easily. A coupling hub whose hole was bored off-center or bored too big, a coupling hub whose hole was bored in at an angle, and a permanently bent shaft. You find these problems using a dial indicator. You narrow down what kind of a problem you have by taking 3 runout measurements at different points along the shaft and coupling hub. That's nice to know, but how do you fix these problems? Well, let's take them one at a time. If you found that you have a coupling hub whose hole was bored off-center or was bored too big, how should you fix that problem? Well, you're going to have to remove that coupling hub, get a new one, and bore the hole correctly this time. If you found that you have a coupling hub whose hole was bored at an angle, how should you fix that problem? Same way. Get a new hub and bore it correctly. What do you have to do to correct a permanently bent shaft? You are going to have to disassemble the entire machine and replace the shaft. How often does a runout condition exist? Well, actually, all the time. Some runout is 1/millionth of an inch. Some runout is 1/10,000th of an inch. Some runout is 1/1000th of an inch, and sometimes a runout is several thousandths of an inch. Everything has runout in it. It's just a matter of how bad it is. In my experience, excessive amounts of runout, that is, any runout that exceeds the recommended guidelines mentioned a few slides back, happens on about 1 out of 10 machines. I'm often asked, why do I take 3 radial runout readings? Why don't I just make a face and a rim runout check? Well, here's why. In the cases for a skew bored coupling hub and a permanently bent shaft, I would observe that both conditions would show a runout for both the rim and the face of the coupling hub. The concern is that I would not be able to tell the difference between these two problems. You do not want to think you have a bent shaft when you really have a skew bored hole in the coupling hub. There is one more critical item that should be discussed. Shown here are the 3 most common types of runout problems that exist from the inboard bearings out to the end of a shaft. The dashed red lines represent the center line of rotation of each shaft. If you remember in the tutorial on alignment tolerances, we discussed that it is important to understand that shaft alignment, in its purest definition, is the process of aligning the center lines of rotation with each other. It was also mentioned that we should be aware that certain points along the length of the shaft may, or may not, be concentric with the center line of rotation of that shaft. We've just covered 3 classic runout problems showing that the coupling hub or the shaft itself may not be concentric with its center line of rotation. Is it possible to perform shaft alignment where a runout problem exists? Sure you can, and that could end up being a big mistake. In the case of the shaft that has a coupling hub which is off-center, we can take another shaft and align the center lines of rotation of both shafts with each other and fulfill the requirements for perfect alignment. In the case of the shaft that has a coupling hub which is skew-bored, we can take another shaft and align the center lines of rotation of both shafts with each other and fulfill the requirements for perfect alignment. In the case of the shaft that is permanently bent, we can take another shaft and align the center lines of rotation of both shafts with each other and fulfill the requirements for perfect alignment. Notice, in every case, the center line of rotation of every one of the shafts on the left are in perfect alignment with the center lines of rotation of the corresponding shafts on the right. Do any of these conditions look correct to you? Obviously not. Why would you want to align machinery with a bent shaft or a coupling hub that is not concentric? When you rotate both shafts together when measuring misalignment, your alignment measurement system is finding where the center lines of rotation are and will ignore any runout that may exist. If you are not checking for a runout condition and only concerned with aligning the center lines of rotation, it is therefore possible to align two bent shafts and never know it. The minute that you start that drive system up, you will realize how big of a mistake that was. It doesn't make much sense aligning machinery that should be repaired or replaced. Rotating machinery that has been in service for a while may have damaged bearings, damaged shafts, leaking seals, and worn-out couplings. Periodic visual inspections and non-destructive testing techniques like vibration analysis can help us understand what problems we have with our machinery so we can pinpoint the defective components and replace only what is failing. When we finally shut the equipment down, a shaft lift check is an easy way to check if there might be something wrong with the coupling and bearings of our machinery. Prior to aligning rotating machinery, we need to ensure that coupling hubs are bored properly and the shafts are not permanently bent. We all need to be aware that shaft alignment is the process of aligning center lines of rotation. Many alignment measurement tools are incapable of measuring runout. The center lines of rotation of our machinery can be aligned and there can still be a runout problem present. You can't just hope that you don't have a runout problem. You need to verify that it is within acceptable limits and, if not, what you need to do to correct it.